You are standing in the hottest place in China. The ground is cracked. The air is so dry it pulls moisture off your lips before you can swallow. The temperature is 50 degrees Celsius. In the shade, there is no shade. This is the Turpan Basin. Less than 16 millimeters of rain falls here in an entire year. That's less than a single glass of water, spread across 12 months. And yet, right beneath your feet, a river is moving. It has been moving for 3,000 years. No pumps, no electricity, no pipes, just 5,000 kilometers of hand-dug tunnels carrying free, cool water through the deadliest desert in China. They didn't build a machine. They turned the mountain into one. Every month, you pay a water bill. The water comes through a pipe. It passes through a meter. The number goes up. If the plant fails, the city fails. We've been taught, quietly and consistently, that this is simply how water works, that it has always been this way, that there is no other way. There is another way, and it has been running for 3,000 years without stopping. Over 2,500 years ago, Persian engineers built what may be the most quietly clever piece of infrastructure ever made. They called it a Qanat, a passive water system that uses nothing but gravity and the shape of the earth to move water across miles of open desert. No energy, no moving parts, nothing to break, nothing to replace, nothing to pay for. This technology traveled the Silk Road into China, where it became known as the Karez. In the Turpan Basin alone, these tunnels stretch over 5,000 kilometers, longer than the distance from New York to Los Angeles. They still supply roughly 30% of the region's water today. In 2025, UNESCO formally recognized the system as an irrigation heritage site. Today, we take this system apart, layer by layer, tunnel by tunnel. We'll look at exactly how it works, why it has outlasted everything modern built around it, and why this system is technically illegal to build in most Western countries right now. 7 chapters, starting where the water starts, not in the desert, but inside the mountain. Here is the first thing the ancient Persian engineers understood, and that most modern planners still get backwards. When you need water in a desert, your instinct is to look for water in the desert. You drill down, you pump, you filter, you pipe, you fight the landscape. The Persians did the opposite. They walked away from the desert entirely. At the base of the Tian Shan Mountains, something happens every spring. Snowmelt from the peaks soaks down through thousands of meters of gravel and rock. By the time it reaches the base of the mountain, it has been filtered clean through stone. It sits in deep underground layers called aquifers, held there under pressure by the weight of the mountain above. The water isn't lost. It's stored. The mountain is a battery. It recharges itself every single year. So instead of digging in the desert where there was nothing, the Persian engineers dug at the foot of the mountain where the water already was. They sank a single vertical shaft, sometimes 60, sometimes 90 meters straight down, until they hit the water table. This shaft is called the mother well. It is the starting point of the entire system. From the bottom of this well, a gently sloping tunnel begins its journey outward toward the settlement, sometimes 10 kilometers away, sometimes 40. Think of a garden hose held at an angle. The water moves on its own. You don't push it. You just give it a path and let gravity do the rest. The mother well is the high end of that hose. The village is the low end. The mountain's own weight creates the pressure. The tunnel creates the path. A single mother well, properly placed, can supply an entire community for centuries. Not because it's magical, but because it taps into a system that refills itself. Every spring, the snowmelt recharges the aquifer. Every day, the aquifer feeds the tunnel. Every hour, the tunnel feeds the village. The cycle runs on its own. There are families in Turpan today whose grandparents, and their grandparents before them, walk to the same stone opening at the edge of their vineyard every morning. Cool water, flowing at a steady pace. No bill, no pump, no maintenance call. The same water, from the same mountain, through the same tunnel, for generations. We've built entire industries around the idea that moving water requires power. The Persians looked at a mountain and understood the power was already there. All they had to do was give the water a path to follow. But here's the problem that comes next. You've found the water. You've started it moving. Now you need to carry it across 40 kilometres of open desert, where the summer air sits at 50 degrees Celsius. An open canal in this heat loses half its water before it arrives. So how do you move a river through a desert without the desert taking it? The Turpan Basin doesn't just steal water through heat, it steals it through air. The combination of extreme heat and almost zero humidity creates an evaporation rate that is hard to fully picture. A puddle on the surface disappears in minutes. A shallow canal loses so much water that by the time it reaches a field a few kilometres away, a large portion of what you started with is simply gone, pulled into the air, invisible, wasted. This isn't just an ancient problem. Lake Mead, the largest reservoir in the United States, has dropped by tens of metres over the past 2 decades. Evaporation and drought. A modern system losing the same battle. The ancient builders couldn't explain evaporation in scientific terms, but they could see it happening. And they solved it with a principle so simple, it almost feels obvious. If the sun can't reach the water, the sun can't take the water. The entire Karez channel runs underground, not in pipes, not in covered canals, in a tunnel dug 10 to 20 metres below the surface. At that depth, the temperature holds steady at around 15 degrees Celsius, all year round. It doesn't matter if it's a 50 degrees Celsius summer or a minus 25 degrees Celsius winter above ground. Down in the tunnel, nothing changes. The water never freezes. It never evaporates. It moves through total darkness, shielded from everything the desert throws at it. Walk into one of these tunnels today and the change is immediate. The heat stops. The noise of the desert drops away. The air is cool and still. All you hear is the quiet sound of water moving over smooth stone. It feels like stepping into a cellar on the hottest day of summer. That feeling, that sudden physical relief, is the entire engineering idea made real. The tunnel doesn't fight the heat. It simply removes the water from the heat's reach. That's why a 3,000-year-old tunnel is still full of water while modern reservoirs are shrinking. It's not a difference in technology, it's a difference in thinking. One system tries to hold water in the open and slowly loses. The other hides the water underground and wins without a fight. The water is now protected. But protection alone isn't enough. The water still needs to move, downhill at exactly the right speed, for kilometres through the dark. And this is where the engineering becomes something that genuinely gives modern engineers pause. Because the precision required to make this work, achieved by people in pitch-black tunnels with no instruments, is a level of accuracy that modern construction struggles to match even with laser-guided equipment. There is a problem at the heart of every gravity-fed water system, and it has no easy solution. The water needs to flow downhill. That much is obvious. But the angle has to be exactly right, too steep, and the water accelerates. Fast-moving water in a sand tunnel acts like sandpaper on the walls. It erodes the base, undercuts the sides, and eventually the tunnel collapses from the inside. Too gentle, and the water slows. Slow water drops its sediment. Silt builds up on the floor. The channel narrows. The flow weakens. Over years, the tunnel silts itself shut. The Karez builders found the precise middle point between those two failures. Their tunnels drop exactly 1 metre for every 1,000 metres of distance, a 0.1% grade. To feel what that means, if you were walking along the tunnel floor, you would not feel the slope under your feet. It is so gentle, it's nearly invisible. And yet it is exactly enough to keep the water moving at the right speed. Fast enough to carry sediment, slow enough not to erode the walls. Across 40 kilometres of tunnel, the total drop might be only 40 metres. The margin for error across that entire distance is measured in centimetres. One section too flat, one section too steep, and the whole system either silts up or tears itself apart. Now consider how they achieved this. No GPS, no laser levels, no surveying equipment of any kind. They worked in tunnels barely tall enough to crouch in, by the light of small clay oil lamps, using two tools, a shallow bowl of water and the lamp flame itself. The bowl, placed on a flat stone, showed whether the floor was level. The flame showed air movement, which indicated the direction of slope. They dug a little, checked, adjusted, dug again, inch by inch, kilometre by kilometre, in the dark, and they got it precisely right. Right enough that the water is still flowing at the correct speed, through the same tunnels, 3,000 years later. Modern tunnel boring machines guided by lasers need recalibration throughout a project. The Karez tunnels were built once, by hand, in the dark, and have needed only periodic clearing of silt, not structural correction, for 3 millennia. The bowl of water turned out to be a more reliable instrument than the engineers who study these tunnels today are entirely comfortable admitting. This precision created something the modern world finds genuinely inconvenient, a system that delivers clean, free water to an entire community with zero energy cost and zero monthly bill. And that word, free, is exactly where the story gets complicated. Because in most Western countries today, what these builders created 3,000 years ago would be illegal to replicate. Water in the modern Western world is not a resource, it is a product. In the United States, the United Kingdom and Australia, groundwater is regulated by the state. Water rights, the legal permission to extract water from the ground beneath your own property, are controlled, licensed and in many cases owned by government bodies or private utilities. In several US states, you cannot legally dig a well on your own land without permits, environmental studies and ongoing metering. In parts of the American West, the doctrine of prior appropriation means that water flowing under your property may legally belong to someone else entirely, someone who filed a claim on it before you arrived. In some states, collecting rainwater in a barrel was restricted by law until very recently. Not because it was harmful, because it was water that wasn't passing through a meter. A Karez system is the opposite of this model. The water belongs to the community. It flows from the mountain to the village, shared according to traditional systems that predate any modern legal framework. There is no meter, there is no bill, there is no company in the middle, and because there is no meter, there is no data, no revenue, and no mechanism of control. In Pakistan's Balochistan province, where Karez systems still operate alongside modern infrastructure, this tension is playing out right now. There are 22 documented legal cases involving Karez damage and water rights disputes. The government has enacted specific legislation, not to protect the Karez as a community resource, but to bring it inside the existing framework of state-controlled water. The ancient system and the modern system are genuinely incompatible, and the modern system has the lawyers. Picture a farmer in rural Arizona. His land sits above a natural aquifer. He knows the water is there, his grandfather used it. But today, if he digs a deep well without state approval, he faces fines and legal action. Now picture a farmer in Turpan 3,000 years ago doing exactly the same thing. His well is still running. His descendants are still drinking from it. No permit was ever filed. No meter was ever installed. The Karez isn't a problem because it's primitive. It's a problem because it's too self-sufficient. A community with a functioning Karez doesn't need a utility company. It doesn't need a treatment plant. It doesn't need a monthly bill. And a community that doesn't need those things has stepped outside the economic model that modern water infrastructure is built on. Free water with no meter doesn't just save money. It changes the relationship between a community and the state. And that, more than any engineering consideration, is why you won't find a Karez being built in the West anytime soon. But the legal question is only half the story. Because these tunnels don't just deliver water, they produce something else, something the builders may not have even planned for. A gift that rises out of the vertical shafts like cool breath from the earth itself. Every few hundred meters along a Karez tunnel, there is a vertical shaft reaching up to the surface. From above, these shafts look like a line of small stone-rimmed holes stretching across the desert floor, sometimes for kilometers. From the air, the whole system looks like a dotted line drawn across the landscape, each dot marking a shaft, the pattern tracing the hidden tunnel below. They were dug during construction to remove excavated earth and to let workers in and out. Once the system was complete, they were left open, and this is where something unplanned happens. The air deep in the tunnel sits at a constant 15 degrees Celsius. The air on the desert surface in summer sits at 50 degrees Celsius or higher. That 35-degree difference doesn't just sit there, it creates movement. Cool, dense air at the bottom of the shaft, warm, light air at the top. A natural draft forms, the same principle that makes a chimney work. Cool air rises through the vertical shafts and spills out at the surface. Warm surface air is drawn down into other shafts further along. The tunnel breathes. Homes built near these shafts receive a steady flow of cool, fresh air drawn directly from the underground channel. In the hottest weeks of a Turpan summer, the temperature inside these rooms can be 15 to 20 degrees cooler than outside. No fans, no compressors, no power bill. The global air conditioning market is worth over $150 billion per year. Entire power grids strain under the load of cooling systems every summer. Cities across the Middle East and South Asia are building new power plants just to handle the air conditioning demand of a warming climate. And here, in the Turpan Basin, families have been sitting in cool rooms during 50 degrees Celsius summers for 3,000 years. Not because they invented air conditioning, but because they built a water system and the cooling came along for free. The water was the goal. The cooling was the side effect. The builders were solving one problem and quietly solving another at the same time, because they built something that worked with the natural behavior of air and temperature rather than against it. When your engineering aligns with the way the physical world wants to behave, you sometimes get more than you planned for. Free water, free cooling, both running on nothing, both still working, but none of this lasts without the tunnels themselves holding together. Sand tunnels should collapse. That's the reasonable expectation. The fact that they haven't, that tunnels dug by hand in loose desert sediment are still structurally intact after 3,000 years, comes down to a recipe, one that sounds like it belongs in a kitchen, not a construction site. The Turpan Basin is not solid rock. It is sand, gravel and loose sediment. Dig a tunnel through this material and the walls want to fall in. Add flowing water and the problem gets worse. Water softens the earth, undercuts the base of the walls, and the tunnel slowly begins to eat itself from the inside. Without reinforcement, a Karez tunnel in this soil would last a few years at most. The Persian builders solved this with a lining material called Sarooj. The ingredient list sounds like someone raided a farmhouse kitchen. Clay, lime, ash, egg whites, goat hair. That's it. The lime and ash mixed with water create a chemical reaction, the same basic process that underlies modern cement, though the ancient builders arrived at it through observation, not textbooks. The egg whites act as a binding agent, filling microscopic gaps in the mixture as it cures and making the final material denser and less porous. The goat hair works the way steel rebar works in modern concrete. Short fibres distributed through the mixture that hold it together under stress and prevent cracking. When this combination cures fully, it becomes a waterproof material harder than the surrounding rock. Here is the part that genuinely puzzles modern materials researchers. Portland cement, the foundation of modern construction, begins to break down after 50 to 100 years. It absorbs water. The internal chemistry slowly fails. Eventually it cracks and needs replacing. Sarooj does the opposite. Submerged in water, the chemical reaction between the lime and the water continues for years, decades, centuries, slowly tightening the structure, filling any remaining gaps, making the material progressively harder over time. Researchers who have examined ancient Sarooj samples under electron microscopes found crystal structures that are dense, uniform, and show almost no degradation after 3,000 years of continuous water contact. Compare that to a modern concrete bridge, cracking after 40 years, requiring steel reinforcement that itself corrodes, needing constant inspection and eventual replacement. The ancient recipe, mixed by hand in a desert, with ingredients sourced from a farm has outlasted every industrial alternative we have produced. There is a tendency to assume that older means simpler, and simpler means less effective. The Sarooj record says otherwise. The builders didn't have a chemistry lab. They had centuries of accumulated observation. What works, what fails, what lasts. The egg whites weren't a guess. They were the result of generations of builders noticing that structures lined with this particular mixture held together longer. The knowledge was practical long before it was understood, and it worked better than the science that eventually replaced it. The tunnels hold, the water flows, the cooling continues. And the result of all of this, the mother well, the underground channel, the precise slope, the legal inconvenience, the free cooling, the 3,000-year mortar, is something that should not exist in the hottest, driest basin in China. The Turpan Basin holds a record most people outside China have never heard of. It is the hottest place in China. Surface temperatures in summer regularly exceed 70 degrees Celsius on the ground. Annual rainfall is under 16 millimetres. The basin sits 154 metres below sea level, the second lowest depression on Earth after the Dead Sea. By every measure, this is a place where farming should be impossible, where permanent settlement should be impossible. Turpan produces some of the sweetest grapes in the world. The region is known across China and Central Asia for its raisins, its melons, its cotton. The grapes grown here have a sugar content among the highest of any variety anywhere. That sweetness is a direct result of the extreme heat combined with the steady, mineral-rich water delivered by the Karez. The same sun that should make this place uninhabitable concentrates the sugars in the fruit to a degree that cooler, wetter climates simply cannot match. The desert, which should be the enemy of the vineyard, is the reason the vineyard is extraordinary. This is what the Karez actually produced. Not just water, not just cool rooms, a complete farming civilization in a place where none should exist. And that civilization mattered far beyond its own borders. Turpan was a critical stop on the Silk Road, the ancient network of trade routes connecting China to Persia, India, Rome, and the Mediterranean world. Caravans crossing the Taklamakan Desert depended on Turpan's water and food to survive the journey. Merchants, diplomats, monks, soldiers, and scholars all passed through. Without the Karez, there is no oasis. Without the oasis, there is no viable stop on the route. Without the stop, the Silk Road's central corridor becomes impassable, and the exchange that shaped the ancient world looks fundamentally different. The Karez didn't just water a garden, it made a node in the network that connected civilizations. What makes this system worth sitting with, really sitting with, is not the engineering detail, it's the underlying logic. The Karez doesn't fight the desert, it reads the desert. The mountain's height provides pressure, the earth's slope provides movement, the depth provides protection from heat. The temperature difference provides cooling. The desert's own extreme sun concentrates the sugar in the grapes. Every condition that should make life here impossible is in the Karez system turned into a tool. The builders didn't overcome their environment. They understood it well enough to let it do the work. 3,000 years after the first mother well was dug, 614 of these tunnels are still delivering free, cool water through the hottest basin in China, not because they've been maintained by modern engineers, but because they were built in such close alignment with the way water, gravity, and earth naturally behave, that the landscape itself has been maintaining them. The mountain still recharges the aquifer every spring. The slope still moves the water at exactly the right speed. The Sarooj still holds the walls together. The shafts still breathe. Nothing has changed because nothing needed to. The Silk Road is full of stories like this one. Systems built so well by people who understood their world so clearly that time simply hasn't caught up with them yet. If that's the kind of story you want more of, subscribe to this channel. Every week, we go deeper into the engineering logic of the ancient world. The people who built things that are still standing while everything built to replace them has already crumbled. I'll see you in the next chapter.